mean free path. We look at a single atom, it heat change direction and speed, heat change direction speed, heat change direction speed, and so on. Okay, so I need a free path of mean average. Okay, average. We continue to examine the motion of molecules in an ideal gas. This figure shows the path of a typical molecule as it moves through the gas, changing both speed and direction abruptly as it collides elastically with other molecules. Between collision, our typical molecules move in a straight line and a constant speed. Although the figure shows all other molecules as stationary, but they are moving in much the same way.
We'll use this molecular motion demonstrator to simulate the increasing speed of gas molecules with increasing temperature. The outer frame shakes back and forth, causing spheres to move and collide in a manner similar to that of the molecules in a gas. If we increase the shaking speed, the spheres move with a higher average speed. The average speed of gas molecules increases in much the same way as the temperature of the gas is increased.
One useful parameter to describe this random motion is the mean free path lambda. As its name implies, lambda is the average distance traversed by a molecule between collisions. Okay, lambda is the average distance traversed by a molecule between collisions. So lambda equal to what? It's the length of path during delta t over numbers of collision delta t. Okay, now we calculate these two. The length of path vector t, okay, is v delta t. We consider, okay, the v its velocity, and we also consider other molecules at rest. If we consider other molecule moves the same as our sample, so this should be reviewed as the v relative is about square root v, square root 2v. Okay. The numbers of collision in theta t can be calculated as follows. A little bit confusing. Okay. Now we look at this one. We focus attention on a single molecules and assume, as the figure suggestion, that our molecules is traveling with a constant speed v average, and that all the other molecules are at rest. Later, we shall relax this assumption. Now, this is our sample molecules, single molecules, with speed v average at that t. And around it, you have some other molecule, okay? In this case, we label red one and blue one. It seems it will hit the red one and not touch the blue one, right? Yeah. We assume further that the molecules are spheres of diameter d. A collision will then take place if the centers of the molecules come within the distance d of each other, like this one. And without outside this range, this d will not touch. Okay. Now, we do different way. Another more helpful way to look at the situation is to consider our single molecule to have radius of d, not diameter, radius of d, and all other molecules to be points. This does not change our criteria for collision. What we find is the number of collision. Okay? Yeah. Now, suppose this one is radius d, so diameter is 2d, and move this direction. Okay? And this one are just point. This point, this point, this point. So what we see that one, and we see that one, all the other molecule in this way. This cylinder is 2D, that means we hit with it. And outside this one, will not touch. Okay, so that helps to calculate how many times we hit all the molecular inside the cylinder. So let's do that one. The number of collisions that occurs then equal to the number of the point molecule that lie within the cylinder. The cylinder size is, this is V delta T, and the diameter is 2D. All the molecules inside the cylinder will hit our sample. Okay, right? Yeah. Now we calculate this one. How many? The volume times the density. Yeah. This volume is this pi d squared, because this is times V delta T. V delta T. This is volume, the green one. Here we put the relative speed. Why? Because we consider other molecules are move at the same way. So the speed have to correct. Okay. And this density, the total number divided by its volume, V. This V actually is this V. Okay. We forget this one. Okay. This one. Now. So lambda equal to, this is the length, V, the T, and this is the n number, that's density, okay? And we see delta T can cancel out, okay? And V relative, in this case, we consider is square root 2 times V, a little bit higher than the average speed, okay? In fact, all the molecules are moving, so we have a correction. V relative is about square root 2V. And when we put this one aside, we get a lambda. We see this lambda, the average distance between the two collisions is inversely proportional to its cross-section, pi d squared. The bigger that one, you get more chance to hit, and the lambda is less. And proportional inversely to the density. The more dense, the more chance you hit, so the less lambda. Okay? It's the number. Okay.
We'll use these small spheres moving in a frame to simulate Brownian motion. The spheres represent molecules of a gas in random motion. When we add a larger disk to the frame to simulate a large smoke particle in the gas, the disk is jostled side to side, just as a smoke particle is jostled by the motion of the smaller molecules in a surrounding gas.
Sample. What is the mean free path lambda for oxygen molecule at the room temperature T 300 Kelvin and pressure P 1.0 atmosphere? Assuming that the molecular diameter D equal to 290 picometer. Picometer is 10 to the minus 12, and the gas is ideal. We know this one, lambda equal to 1 over square root 2 pi d squared NOV. We have this one, D. Right? Yeah, D. You should express in meter. Okay? And we don't know this one, and we don't know this one. Okay? We have to find the V from this T and a P. Now, we suppose you have N more molar material. So V equal to nRT over P. We have a P, 1 atmosphere. 1 atmosphere, you have to express in Pascal, 1.01 10 to the minus C. Temperature is Kelvin. So we get a V proportional to the number N in this one. We have V, we put N. N over V, what is N? N equal to molar number plus Avogadro's over V. And put this one N, we cancel the N. We get N over V is 2.44 times 25 per cubic meter. Then we have everything we put the number. Okay, so that's straightforward. I'm not going to do it. Okay, 2 pi d, you have to write in meter. So this 290 pm equal to 2.8 times 10 to the minus 10 meter. And this is the number. We get lambda equal to 1.1 times 10 to the minus 7 meter. Here, let me explain that one. We say, ideal gas, what do you need? We need air. It's much larger than air. The distance between the molecule, much larger than diameter, okay? And this one is diameter is about 380 times, much larger than D. And now let's see the distance between the two oxygen molecule, air's about 11 D, which is much smaller than lambda and larger than D, okay? So that satisfies the ideal gas stereo, okay? How do we calculate air? Now we suppose the whole volume divided by n. That means that this is V over n is the volume for each atoms. We suppose this is a cubic, so it will be air cubic equal to this one. So this air is supposed to be the length of a cubic and approximately equal the distance between the molecules. Okay, so in this sample we calculate lambda is much larger, 380 D, much larger than D, 11 D, much larger than D. That's it. Question B. Assume the average speed of the oxygen molecule is V 450 meters per second. What is the average time T between successive collisions for any given molecule? At what rate does the molecule collide? That is, what is the frequency F of its collisions? We know this one, V average is 450. Okay, what's the time between the collision? Because between the collision is lambda. Okay, we just calculate 1.1 times 10 minus c, 7 meter, and the velocity 450. So we find each t 2.44 times 10 to the minus second, it has a collision. And 1 over t is the frequency. 1 second, how much times it collision? You find in 1 second it collects 4.1 times 10 to the 9th per second. This is a giga. So the molecule of oxygen in the air is busy in collision. In 1 second, you have a giga times collision, very big.